Right, so that was the last thing. I'll put up answers sometime tomorrow, and hopefully I'll have them graded by Monday, but I'm not sure I would count on it because I have two things I have to grade, and I have to write up partially our final, and I have to write a test for Monday for a different class. So it could be Wednesday. But as I said, it's the last thing, so at least there won't be anything beyond here that you're going to miss. So today what we're going to do is start off with the 3.7 and 3.8 stuff, because there's one thing that wasn't on the test that we should do at least one more example of, and one little thing that we have to add in, and then we'll start 3.9, which is the last thing that could be on the final. We will probably start chapter 1, because if you're going on to Calc 3, it's assumed you've at least seen it quickly, so we should at least look at it quickly. So when they review it for Calc 3, it will be semi-review for you at least. Okay. So 3.7, 3.8. Let me start with an example that was on it and add in a little bit. So these first two parts were actually on it. So hopefully you know how to do this part. So a wire has this density, 12x squared from 1 to 2. How do I find the mass? In some ways, part of it should be obvious, which is integral. So it'll be the integral from the 1 to 2. And what do I integrate? The density, right? So do the 12x squared. Since I'm going to use it, I might as well get the number. Sorry about the extraneous marks as always. So I get 28. Again, something that was on the test yesterday. Let's now find the center of mass. And we're going to start with something similar, but I'll leave a space. So there's the equation for the mass. What else do I put in to get the center of mass? So inside the integral I put, so the 1 over m, and then inside the integral I have to put an x, because that x is the values that we're looking at, which are all the values from 1 to 2, and the 12x squared over the m is the weighted average. Oh, so since someone asked, let me ask again. At least one person said they might not be hearing. Can other people hear me? I got at least one yes. Okay. So you do have a little bit of a way of checking it to make sure you haven't done something badly wrong here, which is the wire goes from 1 to 2, so the center mass better be between 1 and 2, and this is. And since the density is getting bigger as x gets bigger, we'd expect it to be past the middle, and again, it is past the middle. So this was on the test. So any questions on this? This should be hopefully familiar. So let me add in something. And in some ways, if you've done statistics, you should be expecting this, which is the 45 over 28 is essentially the mean. So for people who've done statistics, what tends to go with the mean? And I don't mean the standard deviation, but what other center do you tend to look at besides the mean? No, the median. So we want to get the equivalent of median. And this we can't generalize, so we'll just be doing for the one-dimensional case, but go in. So C so the add-on, we're going to get what's called the mass midpoint, which is another way of doing basically the median. And the median, or in this case the mass midpoint, is a number m so that if I integrate from 1 to m of the density, I should get half the mass. So the mass midpoint is the value so that half of the mass is to the left and half of the mass is to the right, which is exactly what the median is. The median is the number that has half the numbers below it and half the numbers above it. So basically the median. So obviously to do this, we have to first get the mass, which we have. So we found that this is 14. So you'll notice we're instead solving an equation. So bring the 14 down, take the antiderivative of the 12x squared, and plug in the endpoints, and we get an equation that we have to solve. Obviously, if we're going to make you do this, it would have to be an equation you can actually solve. So it can't be something too complicated. So for example, here, there are a couple steps. Right? Add 4 to both sides. Divide through by the 4, and then take the cube root. Which if you're using a calculator, if it doesn't have cube root, you just raise it to the power 1/3. And in some ways, this should sort of make sense. So the last one, the B, the center of mass for the wire is the point where it would balance if you put your finger in the middle. This is the number that has half the mass to the left and half the mass to the right. And those will be different because if you have a point that's further away, it's going to count more even if it's not as heavy for the center of mass. Whereas here, it doesn't care how far things away are. It's just, I want half of the mass to the left of the point and half the mass to the right. So the mean and median tend not to be the same unless the density is symmetric around the middle. So this is the last thing, 3.7, that we haven't done. So any questions on this? And then we've done it, but let me do the other type from 3.7, 3.8. something simple, although I might not do the actual integral anyway. So we have now a plate. So the two-dimensional thing where we assume it has the unit thickness and the given density. So here's the picture. Not to scale or anything. And so to do this integral, we'll have to get the points where they cross. If that's not obvious, set the two equal and solve. And so here again, we'll do the same thing as the last one, find the mass, and then find the center of mass. It's just that the center of mass will be parts. Remember, this one, if you think about it, so this isn't the real first question, which the first question is find the mass. But if you think of what you would have done in Calc 1, then that will let you see that we're adding on each time. So for example, if I was doing the area, I know the area is just the integral over the region over the top curve minus the bottom curve. And so now the question is, what do I add to that to get the mass? So it starts off with this, and I'm going to add in something. So what do I add in to get the mass? Hello? So this is the area. So kind of like the last one, we add in the density, right? So we do the -2 to 3. We put in the density. And this time I won't get the number because I'm going to try to fit the 3 things here all together so we can put it together. So if you think about getting the area, and to get the mass, you multiply that area by the density. If you think about what that's giving us is that area times dx is making it into a volume. So we're doing density times volume. Again, so I can fit things. Shorthand. But let's now find the x-coordinate of the center of mass. And so again, we're adding in. So to go from the mass in part A to the center of mass, what do I add in? And this pretty much is just like the last one. Outside the integral, I have to divide by so it's just this part. So this is the density, and this is the volume of a little piece. So density times volume. And it's the volume because from the one above it, the x plus 6 minus x squared is the area of a little slice, and the dx is the width. I mean, so the x plus 6 minus x squared is the height of a little slice. The dx is the width, and we're assuming the thickness is 1, so it becomes a volume. So what do I add in? And it pretty much is the same as the last one. So I put in an x, so I do the x times the x squared times the x plus 6 minus x squared. And again, it's the same as the last one, except it's more complicated, where that's 3 up there. We're doing the average value of all the x's from -2 to 3 multiplied by the weight, which means I also have to divide by m. So I have that. So we can see, at least for now, it's building on themselves, which is if we start with the area, it's just the top curve and bottom curve. If we're doing the mass, we multiply that by the density. And if we're getting the center of mass, we're multiplying that by x. And finally, for the y-coordinate, in some ways this is now going with b, which is if we want to find the x-coordinate, we multiply x times the mass divided by the total mass. Here we would like to multiply by y, but we can't because that would give us 2 variables, and we don't have a double integral. So again, leave space. So this part comes down. We would like to put a y in front there, but we can't. So do you remember what we put there instead? And I don't think I've, which is the average. Let's see if I have actual space to do this. X plus 6 plus x squared over 2. So yeah, inside the parentheses, there's x plus 6 plus x squared, which is just the top curve plus the bottom curve divided by 2. Remember, the reason we do that is if I draw back up here a generic line at a value x, since the density only depends on x, the center of mass is just the middle of the line segment. And the way you get the middle of the line segment, if it's going from A to B, is A plus B divided by 2. So we do, in this case, the top curve plus the bottom curve divided by 2. Okay. And if, like me, you weren't doing the integral, so if you're not asked to do the integrals, just label things. So in the part A, I labeled the integral for the mass as m. That way I can just use the 1 over m for the next 2 parts. So this would be fine. Assuming you're not asked to evaluate the integral. So any questions on this? So since we had the test yesterday, I'm assuming you hadn't looked at this type of problem from 3.7 and 3.8 because it wasn't on the test. And I assume you didn't do it for today because you had the test. So over the weekend, if you haven't already, try a couple of these examples. We'll do it at least one more on Monday. But let's move on to the last topic that's on the final. So again, any questions on this? Okay. So for us, the last section is work in 3.9. In the section, they do some other things that with kinetic energy and potential energy and stuff like that. You don't have to worry about that. So you can ignore the potential and kinetic energy stuff. So just work. So before we actually do it, let's go back to the basic physics thing, which is, what is work? How do you get work? for people who've had physics. So what is work? So force times distance. In some ways, there's a little bit more to it. So we'll probably get to the chapter 1 thing, which is it really is exactly the force in the direction that we're moving times how far we move, which we'll find out actually will end up being a dot product, which is one of the things we'll do in chapter 1. But for now, let's pretend that we're doing things one-dimensionally, so we don't have to worry about force being in a different direction. So the problem is, of course, the usual integral problem is, what if the force isn't a constant? Then in that case, we can't just multiply. So we're going to have to break up into little pieces, add them all up, which will become an integral. So let's look at an easy example. And for that, we'll use something that has a really easy force, which is, at least for short and medium distance, is a spring. And so here, force required to move a spring x units from the rest position or natural position or whatever you want to call it is just k times x for some constant k. And that k will then be called the spring constant, pretty obviously. So about as easy as a force gets, just a constant times x. So let's use this and talk about how much work it would be to either stretch or compress a spring. It turns out that it's the same equation. We're not going to do from one to the other, because then it gets a little weird, because if I'm stretching and I'm doing work in one direction, if I'm compressing and I'm doing work in a direction, so I get a positive and negative work. So we're not kind of like the rotation stuff. We're not going to do examples where part of it cancels out or anything like that. So let's go to an example. So a fairly big spring. A spring has a natural length of 3 meters. Sorry about, as always, for the things. So a spring has a natural length of, say, 3 meters. If it takes a force of 4 newtons, and I have no idea if that makes sense or not, to stretch it to 4 meters, find the work to stretch it from 3 to 4 meters. So the first little thing is we have to get K, and that's pretty easy. The only thing you have to be is a little bit careful, which is, so the force is equal to 4, and we're going to set that equal to Kx, but x from the last one isn't the position, but how much it's been stretched. So since I've stretched it from 3 to 4 meters, it's been stretched by 1 meter. So it's just K. So in this case, the force is equal to 4x. Okay. And in some ways, you can probably guess. How do you think I'm going to get the work? Go straight to the answer and then talk about why it is. So how do you think I'm going to get the work? Since we're in calculus class. Right, the integral. And like the last one, we just have to be a bit careful, which is we're stretching from 3 meters to 4 meters, but those aren't the numbers we plug in. At 3 meters, the amount that's been stretched is 0. At 4 meters, it's been stretched 1 meter, because x is, again, not the position, but how much it's been stretched. So let's talk about this. So we know that force work is equal to force times distance. So the typical thing is what we're going to do is we're going to start at 0. We're going to break up the line into a bunch of little pieces. On each of the little pieces, we can assume the force is basically a constant. And so we'll multiply the force by that little distance I've moved, add them all up, and then see what happens is that distance gets shorter and shorter. So here, this is the force. This is the distance. So similar to the first mass one, this becomes pretty easy, which is to get the work, we just integrate the force. And as usual, don't worry too much about the units. So I get something like that. Here's the really basic one. And as I said, it's kind of the typical integral thing, which is you break it up into lots of little pieces, you assume the function is constant on that little piece, and then use the usual definition, force times distance. Okay. So any questions on this? Because what we're going to do from now is start making it a bit more complicated. So do, depending on time, 2 or 3 more ones that are getting slightly more complicated each time. If you've done physics, you've probably done more complicated stuff than we'll do. But get to it. Okay, so next one. Example. So a similar question. Again, the force is changing. Here, the assumption we're making is, I'm not sure exactly how you would make this, but you're standing by a hole in the floor. The rope is hanging down, not touching anything. And as you pull it up, what you're pulling up is getting lighter. So you assume that the part of the rope that you pulled up automatically doesn't weigh or anything like that. So again, kind of a simplistic model. And so our first little thing is, so at, and in some ways we have our usual thing, which is if you draw the rope, if you break it up into little pieces, for that first little, so if this is the rope, for that first little piece, I can assume that it weighs 10 pounds. And so therefore or the force for that first little piece is 10. And then after I pull that up, then the rope is a little bit shorter, so it weighs a little bit less. So first little thing is the sorted density of the rope is is 10/50ths or 0.2 pounds per foot. If I have pulled up X feet, then the weight or the force is what? And can do an easy example. If I pulled up 25 feet of the rope, how much does the rest of the rope weigh? Just half of it, the 25. So this would be that. And now we're back to the last one, which is we assume that if I pull up the rope just a tiny bit, that's basically a constant. So I multiply the force by the little distance I've moved it, and I integrate from 0 to 50. I think I brought this up before, but here now we do have to start worrying about whether we're given in something in pounds or kilograms, because again, oh, thank you, yes, much 10 for 10 pounds, thank you. So the little thing is, in terms of mass or weight, which are each of these? So is kilograms a mass or a weight? And are pounds a mass or a weight? So if you're given pounds, that says you're being, oh, so so I notice I corrected it because someone else noticed it should be 10 minus 0.2x. So this is, get rid of all together. So it's 10 minus 0.2x. Is the 10 minus 0.2x okay? Okay. So if you're given pounds, that's a force, which means you just multiply by the distance. If you're given kilograms, how do I make that into a force? I have to multiply the mass by g. So if you're given kilograms, I would have had to put the 9.8 in here. So this one, I'll be my usual lazy self and not actually get the units, but I mean get the number, but I should at least remind you that the units for this are not given a name, just foot-pounds. So whatever the number is. So any questions on this? Kind of next level, but you can see it's pretty similar. Again, the force is pretty simple. It's linear, and we get the weight by multiplying the force times the tiny distance that we moved it. So add a little bit more. So in some ways a similar one, except instead of a rope, we're going to make it a leaky bucket. Assume you're pulling it up with a rope type thing that doesn't weigh anything, so that part we can ignore. And you can see we have something similar going on, which is, again, we have something that as I'm pulling it up is getting lighter. But the little problem is that that's in terms of time. And since I'm going to multiply this by the distance I move it, we have a problem because we're going to get two variables. So we have to get rid of one of them. Luckily, this is a pretty simple one. In terms of time, what is the height? So for the last one, I didn't get a number answer. Usual thing, just setting up. So for the full thing, it's x, but I'm saying what is the height at time t? So let's make it x of t. So what is the height at time t? And this is just a simple thing, which is I'm lifting it at a velocity of 2 feet. I don't say where we start, so let's just pretend it starts at height 0. And therefore, the height will be just the antiderivative, or 2t. So therefore, I can get rid of the t by solving. And plugging it in. And now I'm back to the last problem. So hopefully I've done this right. So the 0.05 there is, there you go. So just adding a little thing where instead of getting the movement in terms of how far it moved, it's in terms of time, in which case you just have to do a simple substitution like we did. So sort of the next level. And again, I'll be lazy. I'm not going to get the number. I will note that in some sense for all these problems, there are always two directions for the work, because as I raise a bucket, I'm doing work on the bucket. But on the other hand, the bucket is in some sense doing work on me. So one of us is doing positive work and the other is doing negative work. So depending on which version you're looking at, we can either get a positive or negative value. So since this isn't physics, I'm not going to worry too much about whether you get a positive or negative. So it could be that we're setting things up backwards. We should go from 20 to 0 or something like that. Here, we shouldn't. But so in other ones, it could be that the direction we look at could be sort of backwards depending on how we look at it. And as I said, I'm not going to worry about it. So any questions on this problem? One more, which will be a simple version of the type that usually ends up being on the final. So I have a tank of water, and I'll be lazy and make it two-dimensional. That is 8 meters tall and has a radius of 2 meters because it's a cylinder. So if I look at a cross section, it's a circle, which I'll draw in a second. And it's filled to the top with water. Then how much work does it take to drain it from the top? First, let's talk about how we would actually do it, which is the easiest thing, of course, would be to drain it from the bottom, put a hole in the bottom. But how much work does it take to drain it from the bottom? 0, because right, you're going with gravity, so you're doing no work. So we don't want to do it there. The other next easiest thing that you would probably do is you would probably put in a pipe that would go to the bottom and drain it from the pipe, kind of the usual way you would do it with a straw or something like that. In that case, it pretty much, since the distance we move each of them is the same, the work would just be the total weight of the water times 8. So we don't want to do it that way either, because that's simple. So in some ways, we're going to drain this kind of in a weird way, which is when we put in the pipe that's draining it, we're going to move it down as we drain it. So we start with the pipe right at the very top, so it drains at the very top, and then as we're taking out water, we're moving it down. That way, the distance that we're moving will change. And we're going to look at this in a different way. We could do this similar to the last couple, but instead I'm going to look at something different. I'm going to, again, do the kind of the typical integral thing, which is break it up into lots of little pieces. But now, instead, you'll notice in this simple example, at least, the force of each of the pieces is a constant. What changes is how far I move it. So let me pull out one of the slices. let me go through the steps. So first let's make this little slice for now delta x, which will become dx. What is the area or volume of this little slice? And you can see, well, it's just a circle, so it's the pi r squared. Officially times delta x to make it a volume, but that is sort of the volume. To get the mass, I multiply by the density. And to make it a force, I have to multiply by, as we did from a couple slides ago, gravity. And this is where you have to be careful, which is if I gave the density in terms of pounds instead, you wouldn't have to multiply by gravity. So gravity in US units is 32 feet per second squared, but you don't need that because if you're given pounds, that's a force, and we don't need the acceleration. And then let me simplify this a little. Well, whatever. It's going to multiply out, but I'll be lazy. So there is the force, and now the work is equal to the force times the distance, which in this case isn't the dx, it's our x. And x goes from 0, I start at the top, and I go to the bottom. And now, as I said, I could do it like the last problem, which I could figure out, well, what is the total mass of the, or total force of the water, the total weight of the water, and then find how much I'm subtracting off. But for the next part, which I'll wait until Monday to do, what we'll do is say, well, what if it's not a cylinder, but what if it's a cone, in which case the radius is changing as we're moving down. And so the two little problems are, one is it's a bit more of a pain to figure out what the total mass is, and the other is it's even more of a pain to figure out how much we're subtracting off as we move down. So it'll turn out that this variation is going to be a little bit easier to do. And for the next one, when I do make it a cone instead, we're going to start using similar triangles. So pretty much that's the next type of thing, which is we're doing the same type of thing, except instead of being a cylinder where the cross-section is a constant, we'll do cones or pyramids where the cross-section is changing as we're moving up and down. Also, we'll talk about going the other way. This is where emptying a tank, it's similar if instead I was building it. Because if I was building it, what I would do is I assume that I'm bringing up one little slice at a time from ground level up to where it should be. So let me stop here. And as I said, Monday we'll make this the more complicated thing where we have to do similar triangles to get the area at a particular value of x. But any questions on this? Partially end early because you have the test, and I don't have them back yet, so sorry about that. But also don't want to go too far. So if you haven't already, as I said, look at the two-dimensional things in 3.7 and 3.8. And if you want, you can start looking through 3.9. And Monday, I'll do at least one more plate one from 3.7 and 3.8, and then go the next level with this last type of problem where the cross-sectional area is changing as we move down. And as I said, that's the last thing that's going to be on the final. next Wednesday and Thursday, we'll look at part of what's in Chapter 1 in the next text, which is going into Calc 3 if you take Calc 3. And as I said, the reason we're going to at least start that is in Calc 3, it's assumed that you've already seen that. And so therefore, you want to at least have seen it quickly so it's not completely new, because we go through it pretty quickly. Okay. So any questions on this? Okay, so the usual thing. If you don't have any questions, we're done. Have a good weekend. And if you have questions, stick around.